Okay, let's get right into it. Welcome back to our latest explainer. Today, we're unpacking a scenario of just unimaginable scale. We are going to mathematically reconstruct exactly what would happen in the first 60 minutes following a hypothetical, catastrophic failure of the Three Gorges Dam. Now, I want to be clear up front. We aren't dealing in speculation, politics, or science fiction today. We're looking purely at the cold, hard physics behind what would be the single largest event release of water in recorded human history.
So here is the monumental question we have to answer. What exactly does 39.3 cubic kilometers of water do in 60 minutes? The sheer scale we're talking about is honestly kind of hard to wrap your head around. The Three Gorges Reservoir sits at an elevation of 175 meters above sea level. It holds back 39.3 cubic kilometers of water. To put that into everyday terms, we are talking about 39.3 trillion liters. If that dam gives way, what does physics tell us is going to happen to the Yangtze Plain over the very next hour? Section 1. Structural integrity and failure modes. Now, in the real world, an instantaneous vanishing act of a structure like this is impossible. The Three Gorges is a concrete gravity dam. It's built on solid granite, rising 181 meters above its foundation. And the physics behind a gravity dam are actually pretty elegant. The dam is basically a gigantic solid wedge. It holds back the immense horizontal pressure of the reservoir entirely through its own downward vertical weight. That massive weight presses against the granite bedrock beneath it, creating enough friction to keep the whole thing from just sliding downstream. Because it relies on this incredible sheer mass, and because it's been continuously monitored for 20 years, the dam isn't just going to magically disappear in a split second. Instead, physics dictates that a failure would happen through a localized breach. But a breach has to start somewhere. It would take an extreme trigger, maybe an earthquake exceeding its magnitude 6.0 design limit, a massive landslide-generated wave overtopping the crest, a targeted military strike, or some kind of progressive hidden structural failure. But if a section does give way, that's when the real danger kicks in. Water immediately rushes into that opening. The massive sheer force of the water acts like a saw, eroding the broken concrete edges and widening the breach incredibly fast. Within just a few minutes, a small failure expands into a gap hundreds of meters wide. Section 2, Minute 0, the breach. Once that gap opens, the water behind it doesn't just sit there, it violently accelerates. To understand why, we need to look at fluid dynamics, specifically an absolutely crucial concept called head. In fluid dynamics, head is just the height of the water sitting above the opening. At Three Gorges, the reservoir is up at 175 meters, while the river downstream is way down at about 65 meters. That means the head, the column of water pushing everything forward, is a massive 110 meters. And a 110-meter head generates a staggering amount of force. Theoretically, we're talking about a velocity of 46 meters per second. That equates to a mind-bending 165 kilometers per hour. Now, realistically, because of friction, chaotic turbulence, and all the jagged chunks of broken concrete in the way, the water won't move quite that fast. But even the realistic estimates put the initial flow at the breach somewhere between 70 and 100 kilometers per hour. That is highway speed. The volume blasting through this gap is literally beyond human comprehension. In just the first 5 minutes, billions of liters of water surge through the breach. The immediate sensory impact of this would be absolutely terrifying. The roar of the water would be deafening. You'd hear it from tens of kilometers away. And the sheer physical impact of that much water slamming into the downstream riverbed, it would literally shake the ground beneath your feet, registering on nearby seismographs exactly like a localized earthquake. Section 3, Minute 5 to 30, the wall of water. Okay, so this is where the theoretical physics suddenly turns into a very grim human reality. The city of Ichang is just 40 kilometers downstream. With this flood moving at 70 to 100 kilometers per hour, the water arrives in roughly 30 minutes. Stop and think about that warning time for a second. Even if the alert goes out the exact second the dam breaks, giving less than 30 minutes to a city of 4 million people, that's not an orderly evacuation. It's an absolute frantic scramble for higher ground. And the thing is, what hits Yichang isn't just a wave of clean water. It's a massive wall of debris. The destructive physics here come down to what's called lateral water loading. Think of it like a liquid battering ram. The impact force of fast-moving water carrying huge chunks of dam concrete, reservoir sediment, boulders, and previously destroyed infrastructure is vastly more destructive than water alone. The sheer lateral force of this debris-laden impact will severely damage or just utterly obliterate virtually every building in its path. Everyday city infrastructure is simply not explicitly designed to withstand lateral water loading of this magnitude. So, as we hit the 1-hour mark, the flood tears past Yachong and spills out into the Jinghan Plain. Here, the terrain flattens out, which means the physics shift entirely. The torrent, which was about 1.1 kilometers wide in the gorge, starts to slow down, but it spreads out laterally. It becomes tens of kilometers wide, burying agricultural land and entire towns under deep, muddy water. It approaches Jingzhou at the 1-hour mark. Now, there are flood diversion areas downstream for contingency planning, but it takes 48 hours for the water to even reach the diversion areas at Shaxi to see any meaningful reduction. That's 2 full days. In Shaxi, it's less than a quarter of the way to the coast. Section 4. The energy scale. Let's step back, crunch the numbers, and clinically calculate the sheer physical energy being released here. We are looking at the potential energy of 39.3 billion tons of water, dropping an average of 120 meters down to the plains below. To find out what that looks like, we use the fundamental physics formula. Energy equals mass times gravity times height. E equals mgh. Simple enough, right? Well, when you actually run the math on 39.3 billion tons of water, you get a result of approximately 4.6 times 10 to the 13th power joules. That equals 46 terajoules of energy. It's a massive number, but humans aren't really great at conceptualizing terajoules, so to really grasp what 46 terajoules means, we need to compare it to something in history. 46 terajoules is roughly equivalent to 11 kilotons of TNT. For some historical perspective, the atomic bomb dropped on Hiroshima was about 15 kilotons of TNT. So the total energy released by a full break of the Three Gorges Dam is literally in the exact same order of magnitude as a nuclear weapon. But there's a really crucial difference in the mechanism of destruction here. A nuclear weapon releases its energy in microseconds, in one single concentrated blast. The dam break releases that exact same amount of energy, but as sustained, relentless flooding, drawn out over hours and spread across hundreds of kilometers.
Section 5. Risk versus consequence.
As the downstream progression continues, the reservoir just keeps draining. It's a domino effect. Wuhan, a city of 11 million people, sits 700 kilometers away and sees a massive, slower inundation within a day. Farther out, Nanjing, 1,200 kilometers downriver, sees river levels rise over several days, completely overwhelming defenses that were only ever designed to handle natural monsoon floods. And eventually, days to weeks later, this massive surge hits Shanghai, where it's compounded by the complex tidal effects of the delta. And here is why this explainer matters so deeply. 400 million. That is the approximate number of people living on the Yangtze Plain between the dam and the sea. Every major city, every vital rail line, every major road follows this specific river valley. This represents the absolute largest exposed population for any single disaster event in human history.
So as we wrap up this analysis, let me be very, very clear about something. The actual probability of this catastrophic failure happening is extremely low. The dam is massively over-engineered. But the physics of what happens if it does fail are undisputed, measurable facts. The volume is a known quantity, the elevation is a known quantity, the terrain downstream is explicitly mapped, and the people are counted. There's no bias here. This is objective, clinical physics.
And that brings us to a really sobering realization, because the consequences are so historically extreme, literally measured in hundreds of millions of lives. Even a minuscule fractional probability of failure demands our attention. It's this exact dynamic between extreme consequence and physics-based certainty that makes this concrete gravity dam the single most consequential structure on Earth. So I want to leave you with this question to ponder. Does looking at the undisputed physics of this scenario change your assessment of the risk? Let me know what you think. Make sure you follow up with us, because in our next explainer, we're going to take a really deep dive into the downstream mortality geography, looking at exactly who is most at risk and why. Thank you so much for joining me today, and I'll see you in the next one.